So, right, so we last time started talking about Hilbert spaces, and we will continue that discussion today. And where we ended up last time is, we define the notion of a Hilbert basis. Okay, so Hilbert basis, okay, was an orthonormal set. Okay, so of arbitrary cardinality, such that it was basic, was the idea. And the idea of basic is such that for any vector v in V, okay, and so I guess I'm talking about an inner product space here, like so. We V is the sum. Okay, and this sum is not necessarily finite. Okay, and one of the things that we saw was that if this is true, then these coefficients C were given by so really this summation is this one. Okay, and that should be a formula which is familiar to you in the finite dimensional case. Okay, so let's look at some examples. All right, so let's remember back now, this is in the now distant past, but we had this subset or this vector space for, and I think I maybe had used the letter J at the time, but it doesn't matter. But for an arbitrary set I, this is the set of mappings from I into the scalar field F, and the superscript 0 here means that the value of the mapping is 0, except for finitely many values in the domain. Okay, so let's write that out. So this is fees from I into F, so that the support of phi is finite. Right? And we had previously put an inner product on this, or we had defined a norm, and that norm was the 2 norm, and that norm comes from an inner product, like so. So sum over I. So phi of I psi of I conjugate. Okay, and so this inner product gives rise to the 2 norm, which is defined in the usual way of a norm coming from an inner product. Like so. Okay. So we had, when we talked about this vector space, we had defined a Hamel basis. And so by that, I mean an ordinary basis, meaning that it's linearly independent and it spans. And we had definitions of what those concepts meant in the for infinite dimensional vector spaces, which generalize things you would already have seen in finite dimensional vector spaces. And so we had so F 0 as the Hamel basis, or again, just basis. But I wish to distinguish it here from a Hilbert basis. And this Hamel basis is defined, the vector EI is defined by EI at J is equal to 1 when I is equal to J and 0 otherwise. Okay. And so the fact that we had stated but not proved, I think I stated this. If not, I'm going to state it now. The fact is that if V is an F vector space, okay, and we had the notion of a dimension of a vector space, and that was just the cardinality of a basis. And it said but didn't prove that some facts about that definition, one of which was the dimension is well defined. So if you have a basis of some cardinality, then any other basis has the same cardinality. Okay, so if F is a V is an F vector space with dimension of V equals the cardinality of I, this index set I, then V is isomorphic to F I 0. Okay, so in some sense, this vector space plays the role of the canonical vector space of a given dimension. Here, that dimension is possibly infinite, uncountable, for example. Okay, so is this basis. So this basis is clearly this set of vectors as a set of vectors in an inner product space with this inner product. It's clearly orthonormal. You can just check that very easily from the definitions. And moreover, it is also clearly a Hilbert basis. Okay, and that's clear because the definition of Hilbert basis is that every vector can be written as a linear combination of these basis vectors, and that's true because these guys are not just are already a Hamel basis, and so I know that every vector V in F0I can be written as a finite linear combination. So in particular, a linear combination. Okay. All right, so in this case, you have the notion of a Hamel basis, and the Hamel basis is equal to the is also a Hilbert basis. Okay. Now that situation turns out isn't such an interesting one, and the reason is, as we've already seen, is that this vector space, in the case where I is infinite, with this norm, is not complete. Okay, so as soon as you ask for completeness, then you're going to have to enlarge this vector space, and so we're going to denote little L2 of I F. This is going to be the set of mappings whose L2 norm, given sort of by this, except now in this situation here, remember, that there's no issues about what this means in terms of convergence of this sum, because the sum is always finite. So phi and psi always have finite support, so the sum will always be finite. So the norm doesn't need any notion of convergence to be defined, unlike the situation that I'm about to write down right now. So the condition that I'm going to put on my phis here, it's that that's true. Okay. So now I'm using these arbitrary sums that I talked about in the last lecture. And so we know what these mean, right? So we had a notion of what it meant for a possibly even uncountable sum like this to converge. And it converged if, given any epsilon, there's a finite or converge to some vector phi, if given any epsilon, there's a finite subset of I, so that the finite sum of these guys is within epsilon of v, okay? or phi, or whatever the limit is that you're proposing. Okay. Anyway, we talked about that sort of clearly last time. All right, but so the point is that this is well defined. It turns out this is also a Hilbert space. So it's complete. Okay, so this shouldn't come as a big shock. We considered this sort of carefully in the case where I was countable. Okay, but it's true for arbitrary index sets, and the proof is not that much harder once you sort of get used to how to do these proofs with this notion of convergence of uncountable sums. It's not much harder than the countable case. All right. Okay, so now, so the question you can ask now is, so is EI a Hamel basis? Sorry, I didn't. Well, actually, I mean, I want both things to be true, but let me first ask this question. Is it a Hilbert basis? Okay, so now, because I'm in a Hilbert space, so last time we looked at these various kinds of properties of orthonormal sets, maximal, total, and so on, and we saw that they agreed for Hilbert spaces. So I'm going to kind of give the, to show that it's a Hilbert basis, I'm going to use the one of the equivalent properties of basic orthonormal sets, and that is that for a basic orthonormal set in a Hilbert space, the only vector orthogonal to the set of basic vectors is the zero vector. And so the answer here, in other words, is yes, because if phi is in L2 of I F, and phi is orthogonal to every EI, then phi is equal to 0. Okay, and so that was equivalent to one of the properties, or that is one of the properties that's equivalent to the set EI being Hilbert basis in the case of Hilbert spaces, not just inner product spaces, but Hilbert spaces. Okay. Good. So this set is still a Hilbert basis for this now larger set, which is, actually, of course, it's the completion of this one in this norm. Okay. So now let's look at the other question. So is this a Hamel basis? Okay, and the answer now is no, because So what you need to do is you need to find a vector which is not a finite linear, a vector in L2, which is not a finite linear combination of these. And you can do that because we find a vector phi in L2. And so I'm here always thinking about I as being infinite, just because the case when it's finite is not interesting. Everything that you want to be true is true. So I'm going to take I as an infinite set. Okay. Okay, so we can find a vector phi in L2 that is a finite linear combination of these guys. Okay, so how do you do that? Well, in the case where the index set is infinite but countable, say the positive integers, then it's easy. So I'm going to kind of reduce it to that case as follows, so that iota be an injective mapping from the positive integers into I. And I know that such a mapping exists because I is infinite, and so it's has at least the cardinality of the positive integers. And so if its cardinality is larger, then I can still find an injection. Okay, and define phi from I to F by. Okay, so phi of index I is going to be a 1 over k in the case where I is equal to iota of k. And k here is, of course, it's in the domain of iota, but just to make sure, emphasize it's one of these positive integers, and 0 otherwise. Okay, so then phi is in L2 because the only non-zero elements in this sum are the countable ones, which are in the image of this inclusion iota. So this is the sum from k over k's in the positive integers of 1 over k squared is finite. Okay. All right, but phi is not in the span of the EIs. Okay, so span here remembers the set of finite linear combinations. And so it's not in the set of finite linear combinations just exactly because of the reason why that this thing is non-zero on this not infinite set, which is the image of iota. Okay, so you can't write it as a finite linear combination of any of those guys. Okay, and so thus this is not a Hamel basis. Okay. All right. So there's a couple of examples to kind of give some meat to this. Okay. So definition. if V is an inner product space, okay, then the Hilbert dimension of V is the cardinality of a Hilbert basis. Okay. Right. So facts. If you have a Hilbert space, then the Hilbert dimension is well defined. Okay. Okay, so if V is Hilbert space, then its Hilbert dimension. So I think I'm going to just roll this into a single fact. Then its Hilbert dimension is well defined. Okay, so that means that if you have two Hilbert bases, they have the same cardinality. Okay, so then its Hilbert dimension is well defined, and is always less than or equal to the Hamel dimension. Sorry, greater than or equal to the Hamel dimension. And moreover, oh, sorry, I had it right the first time. Apologies. And moreover, and we have equality if and only if V is finite dimensional. Okay. All right, and so we see this in our example here, right? So we have a Hilbert basis for this complete normed vector space, Hilbert space, little L2 for an arbitrary index set I. And we have a Hilbert basis, which is this. Okay, but this Hilbert basis is not a Hamel basis. In fact, any Hamel basis must be larger in cardinality than this. Okay. And so this, and so what you see in this example, and as is true in general, is that this Hilbert basis is a Hamel basis if and only if the index set is finite. So what about inner product spaces that are not Hilbert spaces? Okay, so they're not necessarily complete. Well, the proper notion to use there is not the notion of a Hilbert basis, but the notion of a maximal orthonormal set. So remember that a maximal orthonormal set is one that is not contained in any larger orthonormal set. Okay, so maximal with respect to the order of inclusion. And so that notion of maximality is rather similar to what you have for a Hamel basis. So a Hamel basis is a maximal linearly independent set, and a maximal orthonormal set is maximal in the family of orthonormal sets. So, but when you add in the condition of being a Hilbert space, then the maximal orthonormal set becomes a Hilbert basis. Okay, so this notion of Hilbert dimension is most meaningful for Hilbert spaces, more so than inner product spaces. Okay, so I guess I have more than one fact after all. So if B is an inner product space, sorry, Hilbert space, then V is isomorphic as a Hilbert space, and I'll say what that means. To this sort of canonical one that we looked at above. That is to say, there exists a linear isomorphism phi. Let me not call it phi since I've used phi for things in L2. L from V into L2 that preserves the inner product. And what I mean by that is more or less the obvious thing. That is L of U inner product with L of V. Okay, so L is takes values in little L2. So here I'm using this inner product that I defined above. And that's the same as the inner product of U and V in the vector space V. Okay. And so just like this vector space is the canonical vector space of dimension I. Okay, so that's this fact that I stated here. L2 is the canonical Hilbert space with Hilbert dimension equal to I. That's how you should interpret that. Okay. All right, good. So note, and so the point is that Hilbert spaces are characterized by their Hilbert dimension. Okay, and so as a consequence of this, okay. Okay, we can, if V is finite dimensional, then the inner product space, V with its inner product, is isomorphic to Fn with the Euclidean inner product. So, okay, so we talked about that last time. So if V is has countable Hilbert dimension, okay. Okay, so finite dimensional here is unambiguous, whether it be Hilbert or Hamel dimension, because they agree. If one's finite, so is the other. Countable, you must say which one you're using. So I'm using Hilbert dimension. So if V is countable Hilbert dimension, then the inner product space is isomorphic to L2 of F. Okay, so one of these sequence spaces that I defined way back near the beginning of the course, again with the 2 inner product. Okay, and so this is just the space of L2 sequences. All right. So in this case, V is separable. Okay. And I don't want to make a huge big deal out of that, but let me just sort of say what that means. So V is separable, which means it has a countable dense subset. Okay, so dense just means that its closure is equal to all of V. Okay, and so in this case, V is separable. It obviously has a countable dense set, namely the basis itself. Well, that's not entirely obvious, but true. Okay, and moreover, if V has uncountable Hilbert dimension, then V is not separable. Okay, so there's sort of this, one kind of trichotomy in terms of classification of Hilbert spaces. That is, you have finite dimensional, separable, and not separable. Okay, and the finite dimensional case is easy. So amongst the non-easy cases, the separable one is the one people mostly talk about. So you not very often see people looking at not necessarily separable Hilbert spaces, although you can certainly do that, and there's things to do there. But typically, people in analysis who study Hilbert spaces are talking about separable Hilbert spaces. Okay. All right. And so this discussion started in some sense with Fourier series, because we were talking about, or we're going to talk about L2 Fourier series. And there's sort of a general setup for doing that, which is exactly the thing that we're talking about here. Okay, so and there's not much to really do here. So just really, it's just an organization of things we've already talked about. Right, so V is in a product space. And if E is a Hilbert basis, then for V in V, the sum is the generalized Fourier series for V. Okay. Right. Okay, so and again, I will draw your attention to the fact that this possibly uncountable sum has a definition for it. And the reason I want to draw your attention to that again is that in the countable case, so if I, and not just the countable case, the ordered countable case, right? So I is a set of positive integers, then the convergence of the generalized Fourier series can be taken to be in the usual sense. Okay, so I mean, because we have now so many definitions of convergence running around, maybe not so clear what the usual sense is, but I think after I write it, you'll know that this is indeed the usual sense. Okay, so for epsilon greater than 0, exists an n such that the norm with respect to the inner product, of course, okay, so the norm of the difference between V and the capital Nth finite sum, and so sorry, I didn't really mean that. K's finite sum for all k's greater than or equal to n. Okay. All right. And so that's the usual notion of convergence. Okay. Let's talk a little bit about one geometric interpretation of the generalized Fourier series. So the best, and I'll call this the best approximation property. of generalized Fourier series. Okay, so what's the setup here? The setup is an inner product space, just as above. With a Hilbert basis. EI. All right. So for J, a subset of I, let's denote Vj, not little j, big J, to be the closure of the span of the J's for J and J. Okay, so for any set, I'm going to take the span, and the span here means the finite linear combinations of the E's that are indexed by this subset J. Okay, like that. Okay, so now so if V is in V and J is a subset of I, okay, then the vector Vj, okay, which is the sum, the sort of J Fourier series, so the sum over J of V, E, J, E, J, okay, is the unique vector in Vj for which V minus Vj, okay, so this is the norm or the distance of the vector. And so again, sorry, I don't mean little j, I mean big J. Oops. J, okay, is minimized. Okay. All right, so okay, so I take a V and then I let Vj run over this subspace. Okay, and then this particular Vj is the one that makes that distance the smallest. Okay, very good. All right. Okay. The Riesz-Fischer theorem. Okay, so this is kind of like the inversion of the generalized Fourier series, is how to think about what the Riesz-Fischer theorem is. Okay. So let V Hilbert space in this case. With Um, okay. EI, an orthonormal set. Not necessarily anything more than that. Possibly a Hilbert basis, but not necessarily a Hilbert basis. Okay, so if CI is a family of scalars, okay, such that this sum converges, so I shouldn't say it's less than infinity, but because that's not necessarily perfectly clear. So the sum converges in the sense that we've talked about convergence of uncountable sums. Okay, and what this means is that the mapping which sends the index I into the constant CI, that's in little L2 of, okay. All right, so if that thing converges, so then the series also converges. Okay. Okay, and if the limit is V, then of course the CIs are given by the usual formula. Okay, so this particularly holds if these are a Hilbert basis, but it's not required. So certainly it's the most interesting situation when it's a Hilbert basis. Okay, good. Now, given all of that, let's now talk about Fourier series, not in the generalized sense, but in the normal sense. Okay, so normal Fourier series. In L2 per T. Okay. Since that's really what I was wanting to go for anyway, but now we have a lot of infrastructure behind us, and so we don't really need to say very much here. We just have to establish basically that the complex harmonic functions are a Hilbert basis. And then once we show that it's a Hilbert basis, then all kinds of other nice things happen. Okay. So first, note that if, well, let me write it this way. So first note that L2 per T of RC is in L1 per T of RC. Okay, so thus the L2 CDFT can be defined just by restriction. Okay. All right. Okay, so and so in particular, no, I'm going to write something that's obvious, but I want to write it because just to make sure that we understand what's going on. So thus, because the fact is this will not hold for some of the other transforms that we talk about. So it's worth emphasizing this when in the case when it does hold. So thus, if f is in L2 T, then the CDFT of the L2 CDFT can be defined as a mapping and all we know now is that it takes its values in the same place as the L1 CDFT does. We'll just very shortly say more than that. Okay, so the point is that it's just the usual formula for the CDFT. Okay. So note, so first of all, there's a thing that we've used many times. So note that let me first use some notation here. Okay, so let's for A in C, define E A from R into C by E A T is just e to the AT. Okay, so it just gives me a notation for the exponential complex exponential function, and so there's a simple fact that we've verified before, so I'll just restate it here, and that is that the inner product of two of these exponential functions, in the case where A is 2 pi I n over t and 2 pi I n over t. Okay, so it's e to the 2 pi I n over t. So the L2 inner product of two of these guys is t when n is equal to m and 0 otherwise. Okay, and so therefore 1 over root t e to the 2 pi I n over t is an orthonormal family. Okay, so I have this annoying normalization factor out here. Some people take care of that annoying orthonormalization factor by putting 1 over t in front of the integral in the definition of the CDFT, but we'll see that there's reasons why that's not always the best thing to do. Okay. Okay, so this is an orthonormal family. Okay, and so therefore, by Bessel's inequality, okay, I have that for f in L2 per t Okay, so this is a Hilbert space now. Okay, so it's a complete inner product space. Okay. And Bessel's inequality says that the sum of n in Z of the inner product, the L2 inner product of F with these orthonormal vectors. So I'll put the 1 over root t out front here. To the 2 n t inverse. Okay. The 2 inner product. Okay. Squared is less than or equal to the norm of F. 2 squared. Okay, so there's 2 inner products running around here. Okay. This is the discrete little L2 inner product, right? Because this is now a discrete thing. Okay. And then there's the L2 inner product on big L2, which gives the L2 norm, and that's the one I'm using there. Okay. All right. Okay. So just to make sure we understand. So here, this inner product is the big L2 inner product, and the discrete one here is given by the fact that I'm summing. Okay. Okay, good. Okay, and so as a consequence, okay. So what's this? This, of course, is just the, these are just, so let me spell that out. Okay, so since F E 2 pi t inverse, okay, is equal to, by definition, okay, so you can see here why the minus sign is coming in, right? Because of the conjugation in the inner product. Okay, and this, of course, is just the CDFT. Okay, so since that's true, this formula, okay, because F is in L2, this is finite, this implies that the CDFT is in little L2. So the L2 CDFT maps big L2 into little L2. Like so. Okay, very nice. Okay, so now we claim that these things are Hilbert bases. Okay. And so what you have to show is you have to show that, well, there's a bunch of ways to do this. One way to do this is to show that every F in big L2 can be written as a linear combination converging in the appropriate sense of these. Right. We will show that for f in L2 per t r c, the Fourier series of f converges in the usual sense. Okay. And so it's not immediately, it doesn't immediately follow, but it's easy to see that, okay, so here we talked about generalized Fourier series, okay, and I claimed that in the countable case, which is the case we're working in with here, with a countable set, that it's a Hilbert basis, if you have convergence in the usual sense, okay? And so, you know, there's a little bit of vagary going on here because, you know, here the index set is the set of positive integers, and then for the Fourier basis is the set of integers, and so there's a, you know, going off to minus infinity and going off to infinity issue there, and so there's some little ticky-tacky stuff you have to play with. But the point is that to show that it's a Hilbert basis, it's sufficient to show that you have convergence in the usual sense. And so I'm going to make very clear exactly what that means after I turn that into English. Okay. Okay, so that is, we denote by Fn of t to be the nth partial sum. And so, you know, this was the thing that previously we denoted by d per t and f of t. Okay, but that's kind of cumbersome terminology for how frequently we want to use that symbol. So I'm just going to abbreviate the capital Nth partial sum of the Fourier series by f sub n. And just to be clear, that is the Nth partial sum like we have always defined it. Okay, good. All right. Okay, so so one thing I know is I know that by Riesz-Fischer, okay, I know that this sum is converges, so it's finite, being a sum of positive terms. Okay. Oh, I think I maybe made a little typo here in my oh no, sorry, never mind. Apologize. Okay. Okay, so now I know that series converges, and so I get to use that fact. Okay. Now, a direct computation shows that Fn and f minus Fn are orthogonal. Okay, we have explicit formulas for these things, right? So Fn is just that, f is f, and so f minus Fn is f minus that. And so the point is this is a finite series, and so you can just directly calculate everything and show that the inner product of this with this is equal to 0. Okay. All right. So now we have Pythagoras. In Hilbert space, probably true in your product space. Okay, and the way this looks is it's a very simple statement that if U and V are orthogonal, then U squared plus V squared is equal to U plus V squared. Okay, so that's the Pythagoras's identity in inner product space. So this is, A squared plus B squared equals C squared, right? So we're going to apply that in this case. So by Pythagoras, okay, and the orthogonality of Fn and F, we get that. Okay, the sum okay. So this is the, so in the Pythagorean identity here, U is Fn. So, and V is F minus Fn. Okay. All right. So this is, and I guess I probably 1 over T there. Okay. So that's just the Pythagorean identity in the case when U is equal to Fn and V is equal to F minus Fn. Okay. Now we're going to do a little trick here. Okay, so it seems like a kind of random definition, but we'll see exactly. What's the point of defining this function phi? Note that okay. Okay, so let's, what are some properties of phi? Well, so as a function of t, this integrand here is integrable. Okay. Okay, and so, well, in any case, let me. So the fact is that this thing as a function of t turns out to be absolutely continuous. That's not exactly obvious, but but we're going to use that fact. Okay, so we're going to note that, and so it's absolutely continuous, and therefore it's continuous. And phi is also T periodic. So so maybe not note that, because that makes it sound like it's obviously true. It's not. So phi is in C0 per T R. Okay. Moreover, and this is why this definition of phi is useful. You can calculate the CDFT of phi. And it is exactly given by the square of the CDFT of, or the modulus squared of the CDFT of f. Okay, so this is just a plug in the definition of phi and stick in the definition of the CDFT and do some calculation. Okay. All right, so what we know then, so by this fact, okay, so let me call that star. Okay, so by star, okay, it must therefore be the case that the CDFT phi is in little L1. Okay. All right. So therefore, the Fourier series for phi converges uniformly to phi. We saw that when we talked about uniform convergence of Fourier series. Okay, and so therefore we can write phi as its Fourier series. Okay, which you can do if it converges pointwise, but we know more than that. In this case, we know uniform convergence. Okay, and so phi of t is the integral from 0 to t. This is just its definition. Oh, sorry, in the definition of phi, I forgot to put a conjugate there. Okay, so this is just the definition of phi, and this is the fact that phi is equal to its Fourier series. Right. Now, setting t equals 0, we get that the integral from 0 to t f of tau squared d tau, all right, that's this when t is equal to 0 is equal to 1 over t sum and z cd phi over t. Okay, and so that's this when t is equal to 0. Okay, and then using the this fact, okay, this is equal to 1 over t sum z t. Okay. All right, so so what I'm going to do now is I'm going to apply, so this is equal to that, okay? And that, this whole thing, the fact that this is equal to that, this is Bessel's inequality with equality, okay? And so, you know, I can sort of conclude here from my list of statements that are equivalent to something being a Hilbert basis, that, you know, that kind of gets it to me in this case, but let's look at this formula here, okay? All right. So what it says is that this is equal to the limit is, oh, and I made a typo here. Okay, that this is equal to this as capital N goes to infinity. Excuse me. Okay, and so it must therefore be the case that as n goes to infinity, this goes to 0. Okay, so by double star then, okay. All right, and you know, so again, there's many ways to show that something is a Hilbert basis, and this is just one. Okay, good. Oops. All right, so so now lots of different things follow. Okay, so all of the properties of generalized Fourier series apply. All right, so one is that Fn is the best approximation to F in a span E2 I minus 2 pi I n over t E2 pi I n over t. Okay, so this is the first 2n plus 1 harmonics going from minus n up to n. Okay. Okay. The other thing is the inversion formula. So if capital F is in little L2, So this is the Riesz-Fischer theorem. Then some, so let me maybe spell that out, by Riesz-Fischer. And, okay, so this infinite sum converges in L2 and if the limit is denoted by F, sorry, little f, then Fn is the inner product in L2, so integral from 0 to t, f of t. So actually, maybe let me write it down first in inner product notation so that it resembles the previous version of the Riesz-Fischer theorem. Okay, and this is integral from 0 to t minus 2 pi I n t over t dt, which of course is nothing more than the Fourier series, or the CDFT. Okay, so the point is that i.e. Fourier series give the inverse of the CDFT for L2. Okay. All right, good. And so you have to be careful here, because this is a beautiful theory. First of all, you see a nice symmetry with big L2 and little L2. And so, sorry, let me just finish this off. And so punchline, and then I'll start babbling for a second. FCD of F, sorry, from L2 per T into little L2 is a Hilbert space isomorphism. Whose inverse is the Fourier series. Okay, all right, so as I was beginning to say, this is very elegant, okay? It has the nice sort of symmetry to it, L2 to L2. It has very strong properties, so it's an isomorphism of Hilbert spaces, so it preserves the inner product. It has an inverse that we can explicitly write down, okay? So why isn't this just gold? Well, it fails to be just gold because of the really crappy pointwise convergence properties of Fourier series, okay? So this is not as awesome as it seems. since the Fourier series even for L2 does not have great convergence properties. Great pointwise convergence properties. Okay, so what do I mean by that? I mean that, okay, well, let's look back at our discussion now about divergence of Fourier series, which was what we talked about when we initially talked about convergence of Fourier series, because it was good to know what was not true. And so we saw then that the L1 CDFT is a complete disaster with respect to pointwise convergence. So there's F's in L1 per, whose Fourier series diverge everywhere. Okay, so that's just horrid. For L2, it's better. What are the things that we know are true? Well, there's two things that are pertinent here. One is the so-called Carlson-Hunt theorem. And I talked about this before, but it's a long time ago now. It says that if F is in LP per, and the case 2 is of interest to us here, but it holds in this general setting. Okay. All right. So okay. So if this is true, greater than 1. Okay, so if F is in LP for P greater than 1, then the Fourier series for F converges pointwise almost everywhere. To F. So that's the good news. Okay. But the bad news is that that's as good as you're going to get, and it's worse than that. It's as good as you're going to get even for continuous functions. And so again, I stated this previously, but it's good to give it here again since we have a lot more context for what I'm saying now. Right, so there's a theorem of Kahane and Katznelson, which says that there is a continuous, so I'm sorry, I have to say this in its best possible form. I'll say it like this. So if Z in R has measure 0, then there exists an F in C0 per such that the Fourier series for F diverges on Z. So that means pointwise convergence. So pointwise diverges. Okay. And so this is why, when you're talking about Fourier series, from a practical point of view as well as a theoretical point of view, these L2 Hilbert spacey type results are very elegant, but they tell a very weak story, in fact, in terms of being able to practically represent a function by its Fourier series. Okay. Okay, good. So I think that's all I wanted to say about the CDFT. Next time we'll talk about the CCFT, and we're going to go through the CCFT relatively quickly because it has a lot of similarities to the CDFT. A lot of the details, if you dig into the stuff and start doing the proofs, are not quite exactly the same, but certainly many of the results look alluringly similar. And so we're going to rely on that alluring part of it and kind of step over some of the technical proofs. Okay, so that's next time.